In Amazon fulfillment centers, every second counts, and even the smallest error can ripple through operations, leading to costly downtime. Our project, the Parcel Identification and Trackability System, also known as the PIT system, is our solution to Amazon's challenge. In these busy centers, the conveyors are meant only for specific bright yellow totes, as you can see here. These totes carry inbound items to their designated location through the use of Amazon's Ambiflex system. This system is like an escalator for the totes, where it uses stair-stepped wheels to slowly raise the tote to its specific floor. The issue Amazon has is that when any other object enters the line, be it a misplaced box or a stray item, it can cause jams in the Ambiflex wheels and stop it altogether. When this happens, multiple Amazon technicians have to stop the Ambiflex system and pick out all the trash. This delay can cause an effect in operations after the Ambiflex, costing Amazon time and money.
This system is designed to recognize these errors quickly. Once a non-tote is detected, the moving belt is immediately stopped. This halts the error from cascading downstream. At the same time, an alert is triggered that lights up the touchscreen in orange, activates an and-on stick, and stops the belt, all within a fraction of a second. This project not only helps protect expensive equipment and saves time, but also improves overall workflow and customer satisfaction by keeping operations running smoothly.
Now, to meet the team behind this innovative solution:
Adam Fiesel, Systems Engineer.
Andre Fanning, Engineering Management.
Casey Fulbright, Team Lead.
Karcheski, Software Liaison.
Rebecca Gearing, Procurement Lead.
William Rains, Software Engineering.
Ryan Wells, Industrial Engineer. Together, we combine our knowledge of hardware, software, and field testing to bring the PIT system to life. Before building anything, we had to understand the challenges and background of our project. Our project requirements were driven by 3 essential goals, and here's why they matter. First, fast, accurate detection. The system must distinguish a bright yellow tote from any stray object with at least 98% accuracy. Test data confirms that our PIT system not only meets, but exceeds this target. Second was an instant response. In the high-speed environment of a fulfillment center, every fraction of a second matters. Our benchmark required a maximum processing delay of 2 seconds. We felt this was enough to make sure that the non-tote did not make it to the Ambiflex system, when in reality, our test recorded a response time as low as half a second, ensuring prompt halting of the belt and immediate alerting. This was vital for preventing error propagation. Third was a clear notification for the worker. To ensure quick and simple notification, the system triggers 3 alerts when an anomaly is detected. First, the touchscreen alert. This is a display that turns orange until reset. Second is an and-on notification, which is a 2-tier light, which immediately signals a worker. And third is the belt stop, which sends a 24-volt signal from the orange pie to the conveyor and stops it. The combined effect of these features ensures that each detected issue is handled swiftly, minimizing downtime and ensuring smooth operational flow. Our PIT system combines robust off-the-shelf components with custom integrations into 3 main subassemblies. First is the camera subassembly, which is the most important subassembly as it is the eyes of our system and allows us to differentiate between a tote and a non-tote. To do this, we used a Cognex IS2000M along with the Cognex Insight Explorer 5.6.1 software to create jobs. Jobs are a set of tests and checks that allow us to determine if it's a tote or a non-tote. The logic is as follows. If both the front and back edges are detected and the object breaks a central reference point, the center line of the camera's view, the object is verified as a proper tote. If either condition is not met, the object is classified as a non-tote. In such cases, the camera sends a 24-volt signal to the orange pie, triggering the downstream alerts and belt stop. We then have our processing subassembly, which is an orange pie 5 serving as the system's brain. It reads the incoming digital signal from the camera, and if the criteria aren't met, immediately communicates with the existing PLC via an Aussie cable to stop the belt while concurrently updating the touchscreen display. The onboard algorithm is simple yet robust, ensuring that only validated error triggers the notification, reducing the chance of false alarms. Finally, we need some way to hold all of these parts in a secure manner while in a high vibration environment. For this, we used a 1-inch C-channel strut system. This lightweight, easily adjustable frame allowed for easy scalability, while meeting our requirements of robustness. After 3 weeks of real-world testing, we verified that there was no measurable movement or misalignment, confirming our design's vibrational resilience.
Developing the PIT system was an iterative process involving extensive testing and verification, ensuring it met every requirement before deployment. Even though our sponsor, Amazon, is everywhere throughout the country, our sponsors are from the fulfillment center in Goodyear, Arizona. This means to get a perfect testing environment, we would need to drive about 3 hours one way to the facility. We knew this wasn't going to be possible, so with limited access to the facility, we began by setting up our prototype in a controlled environment. In a makeshift lab at Will's house, we built the basic frame and integrated the camera and processing unit. This phase allowed us to verify core functionalities such as basic detection and response times, laying the groundwork for further development.
Once our preliminary tests were promising, we moved the system to an actual Amazon facility for real-world evaluation. Originally planned for a week, our system stayed on-site for over 3 weeks. Here we ran repeated tests under actual operational conditions, using standard Amazon conveyor belts, totes, and ambient conditions to validate performance and speed, accuracy, and reliability. We conducted over 100 trials comparing identified parcels against known correct outputs. Our acceptance test confirmed a detection accuracy of over 98%. A pivotal change during testing was switching from continuous video recording to a photo eye-triggered image capture. This reduced the processing overhead significantly, allowing our detection software to work with standardized inputs and drastically improve overall accuracy. After 3 weeks of rigorous testing, refinement, and data analysis, our PIT system now stands ready for deployment in the real world. In our final test at the Amazon facility, when a non-tow object passed under the camera, it broke the photo eye laser beam. This triggered the Cognex IS-2000M to capture an image. The camera processed the image in real time, detected the non-tow, and sent a stop signal to the PLC in about 0.5 seconds. Simultaneously, the andon light was activated and our touchscreen GUI displayed an immediate alert for the operator.
These results confirm that our system not only meets but also exceeds our core requirements in speed, accuracy, and clarity. What began as a classroom concept has evolved into a fully functioning industrial solution, one that is protecting operations, reducing downtime, and ensuring that every second counts.